Okay, so last time we were talking about Gauss's divergence theorem, and I'm going to go through the ideas that motivate that theorem again, just very quickly as a reminder, and then we're going to go on and talk about a bunch of applications of it, which are really interesting, a lot of applications in physics and engineering. So here's our picture. We're considering a solid three-dimensional region like this that has a boundary. Of course, is a surface. It's an oriented surface, and we're going to be interested in computing the flux of a vector field, some vector field, through that boundary surface. And the idea is, much like many of the other boundary theorems that we've talked about so far, we're going to try to rewrite this as a triple integral, with the hope being that we can start by taking the entire solid and breaking it up into a bunch of little smaller chunks like this. And the hope is that the smaller pieces, that the boundary flux through those smaller pieces, when you add them all up over the entire solid, that in total that will give you the boundary flux through the entire solid. Now the big question on that is, does boundary flux accumulate? Here's our goal. This is what we want to be true. Put a question mark there. Does boundary flux accumulate? Well, the concern is that there are these interior faces, and that interior face is part of the boundary of these little small pieces that we've broken the solid up into, but it's not part of the boundary of the original solid. So it seems like we're introducing new terms here, but as before, what we are going to find, what we have found, is that that face, thought of as part of the boundary of this block, is oriented that way, but it can also be thought of as part of the boundary of that block, for which it is oriented that way. So this face, this green face that we have here, which is part of this summation, that face is going to appear twice in that summation. It's going to appear with opposite orientations. Therefore, those two fluxes are opposites of each other, and in the summation they cancel. So this, again, we've seen this happen many times, geometrically differently, of course, in our previous boundary theorems, but kind of morally sort of pretty similar, really. Okay. Right. So that allows for this calculation here. Boundary flux is a sum of boundary fluxes over the little pieces that we've broken the solid up into. If something's true for all values, it's true in the limit. This looks an awful lot like a triple integral. Not quite exactly, of course, because there's no dv over here, so we multiply and divide by delta v. Now this really does look exactly like a triple integral. The big looming question is, in the limit, in the limit, what is the value of that expression? So what is our integrand for this triple integral? So this is a detailed calculation that has some value and is worthwhile, but it's just, given the time constraints that we have in Math 212, we're not going to go through that detailed calculation in this course. The punchline is that it's computed by that formula. So this goes there, and there then is our result. And we have in fact computed boundary flux as a triple integral over the interior. Now we talked last time again about this notational convenience. This looks kind of like that del operator that we saw previously. That del operator dotting with our vector field. And yeah, it's suggestive anyway of what we're computing there. So this extremely common notation for this expression. This is called divergence. That's the divergence of this vector field whose flux we're interested in computing. And that then, this divergence, represented by that little notation there, that is the operator that's complementary to the boundary operator in making a theorem here. So I'll write the theorem. Here's the theorem, Gauss's divergence theorem, and you can compute a boundary flux. Now, critically, can't emphasize enough, this only works for fluxes through boundaries. Had to be a boundary because we need to know the solid that it's the boundary of to chop up into little pieces to turn it into a triple integral in the first place. So boundary fluxes can be computed as triple integrals of this divergence operator. Okay. Right, and we did an example here last time. So I want to talk about how to think about this geometrically, physically, various applications that we can do with this. I'm going to start off by trying to motivate this terminology called flux density. So flux density, I'm going to skip down here actually and start. So I'm going to segue into this by making an analogous argument about interpreting an analogous theorem, the fundamental theorem of calculus. So here's the old fundamental theorem of calculus. Everybody knows this result. We have taken a different point of view on the fundamental theorem of calculus in this course. And the point of view that we've taken is that this is a way of computing what I am calling change. And I'm going to refer to change here. I'm going to designate it with this Greek letter capital delta. Which is a common choice. We use delta to represent change. We use it as a little prefix for something else to represent the change of that thing. So here I'm just going to use it to represent change. Call it delta, single letter. Okay. So change, as we saw at the beginning of this chapter, is an accumulation of little changes that happen over the interior. So we can think of the fundamental theorem of calculus as being a statement about something that's computed on the boundary that actually accumulates over the interior. Okay. Now that being said, let me remind you how we compute mass. Here's an old hat formula for how we compute mass. It's integral of density, in this case, single variable as it is. That density is mass per unit length. Right. And we can represent that mass differential as density times dx. So we have this formula for our mass differential, and we have this formula, namely the accumulating quantity of change there, is f prime dx. So looking at these two formulas, what we see is that the derivative here is playing a role analogous to density. Now, we don't normally think about the derivative this way, but this is actually a pretty good way to think about the derivative. Let me draw a little picture here now. We're going to draw y as a function of x here. And let's see here. Here is our curve. Starts at A, ends at B. And suppose we are interested in the amount that the function changes between that starting value and this ending value. So there's your f of b, here's your f of a, and change is that. Well, pretty reasonable to make the observation that that total change is the sum of the little changes that get made along the way. So change accumulates. And with that point of view, what would we call the associated density of that accumulation? Well, looking at this little triangle here, change is the rise. And then we say per unit size. Size here is length, which is the run. In fact, rise over the run, what we normally call the derivative that slope right there that we normally call the derivative, rise over the run is change per unit size. And with our general point of view on density, as thinking of density as, well, stuff per unit size, change per unit size could be thought of as change density. This is actually, again, a really reasonable point of view on the derivative. It's how much of this accumulating quantity of change is happening per unit size as you move from A to B. So, again, a very unusual point of view, way to think about the derivative and the fundamental theorem of calculus, but it's a great segue, sort of stepping stone to making an analogous interpretation of Gauss's divergence theorem. So you might want to chew on this for a little bit of time, give this a chance to settle in, thinking of the derivative as change density. Right? And now we're going to make an analogous argument for the Gauss's divergence theorem. So here we go. Here's Gauss's divergence theorem. Oh, I wanted to highlight. All right. Gauss's divergence theorem. So boundary flux is computed with a triple integral of divergence. Right, fine. So now, conveniently, we already have a single character name for that boundary flux. We call it phi. And the way that we got this theorem in the first place was making the observation that phi accumulates. Right? So the result is, what we've found with Gauss's divergence theorem is that the amount of accumulating boundary flux on each interior piece is computed as divergence times dV. So we write that like so. This is just a little formula for the small amount of flux that accumulates on any given little piece of volume. All right. And now let's compare that again to an old calculation about how we compute mass. Well, now this is a three-dimensional solid, so mass over a three-dimensional solid would be a triple integral of density. Density here now is mass per unit volume. And in that accumulation, this mass differential we would write like this. So again, we have an analogous sort of connection. Divergence in Gauss's divergence theorem is playing a role analogous to density, analogous to mass density. So mass density in this mass calculation is mass per unit volume. Divergence here in this flux calculation is flux per unit volume. And again, thinking of density in a more general sense of stuff per unit size, flux per unit volume, very naturally in this case would be viewed as flux density. So that's where this term comes from, this term flux density. We think of divergence as an actual kind of a density. Let me start off a little bit further back. We think of flux, this thing that we're computing here, even though it is actually computed on the boundary, we think of it as a kind of a stuff that's actually almost physical. It's not physical, of course, but we're going to think of it as if it's kind of physical and actually accumulating over the interior in the same way that change is. Now, let me just remind you, it's actually geometrically pretty satisfying to think of change as something that accumulates. Now, yeah, it's computed on the boundary. Sure, it's computed by looking at the endpoints A and B only, and yet we have a very satisfying geometric sense that change actually accumulates as you move along in the interior. So in the same sense that change accumulates here, flux, this boundary flux, actually accumulates over the interior here. So thinking of this boundary flux as an accumulating stuff, the density of that stuff is divergence. So this term flux density, very natural. Very weird point of view. It takes a little bit of getting used to, but take the time, rewind this video recording if you have to. Think about it again, write some stuff out, come to office hours. It's a very natural point of view and way to think about this. Now I'm going to take this opportunity to also talk about an analogous argument for Green's theorem. Let's think about, what does Green's theorem compute? What is Green's operator? What does it look like? What is it, geometrically? How do I think about Green's operator? We didn't talk about this back in the section on Green's theorem. Well, there's Green's theorem. Note we're computing a thing. This thing is computed on the boundary. We're thinking of it as accumulating over the interior. Again, very, very analogous. So this thing that we're computing on the boundary, we have a name for it. Now it's so this is a vector line integral, but the boundary around which we're computing that vector line integral is a closed curve. So what we're computing here then is circulation. This object we're computing is circulation around the boundary curve. So remember now what we're thinking of. We're thinking of the vector field as representing the flow of a fluid. The flow of a fluid, a line integral. When you're talking about a flow of a fluid, this line integral measures the extent to which the fluid is flowing along the curve. And if you're talking about fluid flowing along a curve, and if the curve is making a loop, then what you're measuring is to what extent is the fluid flowing around in a loop. And so again, circulation is a very natural choice of words. Okay. So along those lines, thinking of circulation as something that accumulates over the interior. Well, let's do it like this. Circulation is an accumulation over the interior. Then we have a formula there, Green's operator times dA, for the accumulating bits of circulation. Mass being computed on a two-dimensional sheet by this very similar formula. Again, you see that Green's operator is playing a role analogous to density. So Green's operator, in this sense, can be thought of as circulation density. So we don't think of circulation normally as a stuff, as a sort of a semi-solid physical sort of a thing. And of course, it isn't really. Circulation, in fact, is computed on the boundary. But because of the fact that it does accumulate over the interior, we can think of it as a kind of a stuff, and it's in that sense that Green's operator is circulation density. Okay. Right, now another word for this is vorticity. I think it's a lovely word. The idea there is that if you have a vortex, a whirlpool or a tornado or something like this, so if the fluid really is sort of flowing around in a circle, well, circulating anyway, then at a given point where you might happen to be, if you were to look just in that vicinity, the fluid might not make it around a complete circle, and it doesn't have to, but the point is that locally there's going to be a certain amount of sort of partial circulation that's happening near there. And so vorticity is in some sense measuring to what extent of the total vortex realized over an entire region, in some sense, what portion of that is happening near the point that you're talking about. So again, vorticity, very natural term there. Okay. All right, so I'm going to talk about some applications to physics now. Actually, the rest of this lecture is going to be applications to physics. The first one is I want to talk about fluid flows and how we can use divergence and Gauss's divergence theorem to represent physical quantities. So let me give myself a little bit of room to draw here. I'm going to add a page. And let's talk about a little region of space. Use this color. A little region of space there. And let's imagine that there is a fluid flowing, and I'm going to draw the fluid as flowing out of this region. That's what flux looks like. This is well, let me go ahead and do this. It's a three-dimensional region of space. Okay. Now, ignoring the fact the mass is moving, let's write down a formula for how we would compute the total amount of mass in that region. Mass, whoops, I'll go back to the blue here. Mass is a triple integral of density dV. Old news. Now, let's take a time derivative of this to acknowledge the fact that, well, the mass is moving around here, and so we'll take d by dt on both sides and get dm dt equals triple integral d density dt dv. And for reasons that'll become clear in a moment, I'm going to put a minus sign on both. I'm going to multiply both sides of this equation by -1. Okay. So the reason I want to do this is let's talk now about what this has to do with flux. What would flux have to do with this picture? Well, flux in this picture is the rate at which the fluid is flowing, as indicated here. That's flux. But notice that that is the rate at which mass is leaving this region. So flux is the rate that mass inside the region is going down. So negative rate of change of mass is the rate that the fluid is flowing out. So that negative dm dt could be interpreted as representing flux. Now let me write that down, and so I'm going to do this in a different color. I guess I'll do this in red. Whoops. So flux through that region, and Gauss's divergence theorem tells us that this is a triple integral of the divergence of the flow field dV. So looking at this expression, if flux is negative dm dt, so these two objects are equal, then these two integrals are equal, and this gives us a natural interpretation of divergence. In this little metaphor, divergence is related to the rate that density is changing. So again, you've got this scenario here. We've got a certain amount of mass in this region, a certain amount of mass in here. As mass flows, at any given point, the density of mass at that point is going to be changing. So maybe as mass flows out, the density is going to be going down. Well, if your vector field F, if this represents the flow of the fluid, then divergence is the rate of change of density. Now there's a minus sign because positive divergence means mass is going out, which means the density is going down, and thus density dt would be negative. So divergence is the negative there, but other than that minus sign is a very natural way to think of divergence. Is it's the rate of change of density. I like to call this, or think of this, as a rate of decompression. Right? If the density is going up, then the mass is being compressed, and if the density is going down, then the mass is being decompressed. So you can think of divergence as being a sort of a local decompression rate. Okay, right. Now, I'm going to draw a different picture now, actually a very similar picture, but it's going to be a very different physical metaphor. Different way of thinking about fluid flowing. I'm going to draw a line here. Go all the way down. Okay. So again, I'm going to think about a region of space. Maybe I'll draw this one a different color, just to distinguish it. And we have a fluid flowing. I'll draw this one in yellow, let's say. Okay. And again, I'm drawing the fluid flowing out because that's what flux looks like. It's going to be a convenient picture. So the new assumption that I'm going to make, two new assumptions actually. In our old scenario, this original picture we were looking at, we never really quite said it, but it was sort of implicit that there was only so much actual mass in this picture. There's a certain amount of mass, and we're talking about how does the mass sort of flow around, but there's a fixed amount of mass. And so if there's a flux out, then that amount of mass on the inside, the density of the mass on the inside has to be going down. Right, fine. Okay, so we're going to change our assumptions a little bit. In this new scenario, we're going to allow for the possibility that new fluid, new mass of fluid, might be able to spontaneously generate or sort of appear out of nowhere magically. Whatever. That's anyway. Obviously not a real word, magically, but it's going to. We're going to be able to new mass is allowed to be just spontaneously generate and appear at a point in space. Okay. The other assumption that we're going to make in this new scenario. Let me write these down. So we're going to have spontaneously generating mass. The other assumption we're going to make is that this is a steady state flow. I said differently, we're going to think of this as an incompressible fluid. So now this is again not the case with all fluids. If you have a flow of air, air flowing around, if under the right circumstances, air can compress. And you can have a greater density of air if the air is all sort of rushing inward toward a single point, for example. Or density can go down if the air is all rushing out away from that point. So I'm going to say no more of that. We're going to assume that we have an incompressible fluid, kind of like water, for example. Or depending on what fluid you're talking about, I'm going to say we have a steady state. So in particular, the density is not changing. The density is fixed and constant as time passes, and yet the fluid is flowing around. Okay, so under these new assumptions, what would we make of this scenario where there is fluid flowing? How could this be? How could there be fluid flowing out of a region where the density inside the region is not changing? The density, I'll go ahead and color this in. That density is fixed and constant and not changing, not allowed to change. And so where's this fluid coming from? Well, this fluid is the mass that's being spontaneously generated. So that's going to give us a different different way of thinking about different way of thinking about flux, and resulting a different way of thinking about divergence. So let me write down some of the same equations that I've already written down. We're just going to make a different interpretation now. So yeah, here we go. I'll do this in. Let's do it in. Yes. So mass. Triple integral of density. This time I'm going to write density a little bit differently. I'm going to write density as mass per unit volume, like so. And now again, let's take the time derivative on both sides. So dm dt equals. Now this time the time derivative I'm going to put on the dm. So I'm going to rewrite our integrand as dm dt per unit volume. All right. Now, in this scenario, keep in mind our new scenario, the density is constant, so the actual amount of the fluid doesn't change. The actual amount of the fluid is constant, not allowed to change at all. So if there is a flux, if there is a flow of fluid out of there, what that is telling you, where's that mass coming from? All this mass that's flowing out of the region is mass that is being generated. So that's the interpretation I'm going to take of dm dt. dm dt is telling you how much new mass is being introduced into this system new mass that has to be introduced into the system, because look at all this mass flowing out and not leaving any holes, not leaving any gaps, the mass in here being constant. Okay. So now again, let's write down Gauss's divergence theorem on this picture. Oops. So flux equals triple integral divergence dV. So if flux is dm dt, if flux is the new mass that's being introduced, that has to be introduced so that mass can in fact flow out, density on the inside being fixed, required not to change, then these two integrals are equal, and that gives us an interpretation of divergence. So in this case, divergence, you can think of divergence as, well, it's a kind of a density, something per unit volume. And what is it a density of? What is this expression? dm dt. dm dt says how much mass is coming into the system. So dm dt per unit volume says how much per unit volume in the given region of space, how much new mass is coming in that little region. So there's a terminology for this. dm dt, the total rate that mass is coming into the system, we call that the source. So there is a fluid source here. That's, new mass of fluid is being generated, and this is a source of mass. And along those lines, it makes sense to think about divergence. If flux is source, then divergence is source density. And that's a nice way to think about divergence. So now be careful with your interpretations. Keep in mind these two little scenarios make different assumptions about what's allowed in your little model. On the first side, over here, our first little model we created, well, we assumed that the total mass in the system was fixed. Total mass isn't allowed to change, and so mass leaving means less mass on the inside. And so divergence relates to how density is changing. In this second model that we created, the total amount of mass is not constant, but the density inside of here is constant. So new mass then could be thought of as the flux itself. Flux flowing out is the amount of new mass that's being introduced into the system, and thus giving us this different interpretation. Okay, so these are common interpretations of flux and divergence. Flux represents the extent to which you have a fluid source. By the way, the opposite, when the flux is negative, we call that a fluid sink. In other words, there's a bunch of fluid all flowing into one sort of region and disappearing. So the word sink is extremely relatable, right? This is like a kitchen sink. So sources and sinks. And in that metaphor, divergence can be thought of as source density. Okay. So, moving along, more physics applications. I want to talk about gravity. We're also eventually going to talk about electric fields and magnetic fields, but I think there's a lot of benefit in talking about gravity first. The reason for this is that gravity is just so relatable. I mean, you encounter and deal with, experience gravity every day. Right? You walk around, you're having to balance because you're opposing a force of gravity. If you throw something up, it comes down because of gravity. It's hard to not notice and have a good physical sort of intuitive sense for gravity. So I'm going to do these calculations in the context of gravity first, and then I'll move on to electric fields after that, and eventually magnetic fields. But what we're going to find is that doing gravity first has some nice benefits, and it makes a strong connection to these other forces. So here we go. Now here's the old formula for the force of gravity. In particular, notice that it is an inverse square force. So the force goes down with the square of the distance separating the two masses, proportional to the two masses themselves, and then there's Newton's gravitational constant right there. Okay, old formula, high school physics. So I want to rewrite this a little bit. I want to write this as a vector field, and if I want to think of a vector field as something that is generated by a single mass, I want to think of it as being intrinsic to the mass that is generating the gravitational field. This has to be something which I can write down only in terms of that mass. So you'll notice that in this formula that I've written down, there is no second mass. And what that means is that what I'm writing down here is not exactly a force. This is a vector field, but it's a vector field that instead of representing force, this is a vector field that you would multiply by the second mass to get the force. So I want to think of the gravitational field as independent of that second object. You multiply it by the mass of the second object to turn it into an actual force. Okay. Now, this formula does look problematic. In particular, you notice that there's a cube down here where there's only a square there, and that seems weird, but let me observe that I can rewrite this. Whoops, bad color choice. I can rewrite this as negative g m1 over magnitude of x squared, and let me pull out the vector and the other factor of magnitude of x. And what you see here is that where that cube comes from is that I'm multiplying this unit vector direction times an inverse square, a truly inverse square magnitude. So this what I've written down here. Whoops. What I've written down here is an inverse square field. It just kind of ends up looking differently because I'm multiplying by this unit vector. Okay, and this, of course, is the unit vector that's pointing radially. If you have mass located at the origin, then the force is going to be it's going to be in the same direction as the position vector for that point. And so x divided by the magnitude of x is a unit vector pointing in that direction. Okay, now you've actually seen this vector field before back in the section on partial derivatives. And I didn't describe it as such at the time, but there's an exercise in that section where there's a vector field that looks morally just like this. Now there's a different constant, the g and the m, etc. Those aren't there. I think I just called it k or something like that. But in particular, position vector x divided by its magnitude cubed, that exact algebraic structure is one of the vector fields that shows up in an exercise back in partial derivatives section. In particular, you computed the divergence in that exercise of that vector field. And weirdly, you get 0. Now, that's away from the mass, keeping in mind the mass is at the origin. The vector field isn't even defined at the origin. The divergence is certainly not defined at the origin. So no comment about the origin itself, right? But at points away from the origin, so in particular, when you're away from the mass, the divergence of the gravitational field is 0. That seems really surprising. I mean, the gravitational field, when you look at it, look at this formula. It looks pretty complicated. What are the odds that its divergence would be exactly 0 away from, almost everywhere, in other words. Everywhere except where the mass actually is. That's a very surprising fact. And it's not just surprising, it's also really, really important. It's a very valuable computational tool. This is going to be the main computational tool that we're going to use in doing some really impressive calculations here over the next couple of minutes. So let me dive into the first one here. I'm going to scroll down to this picture. I'm going to consider this scenario where we have a mass located at a point there. And then we have a surface. Now this is a closed surface in particular. So said differently, it's a boundary of a solid region. So I'm just going to call it boundary R. So R is this region on the inside. Right. And having a mass, having a surface, the mass creates this gravitational field. And now we have a vector field and a surface, and it's reasonable to ask what is the flux of that vector field through this surface. Now this looks like a pretty hard problem. Let's take a moment to acknowledge this. Look at that vector field. That vector field points in different directions at different places. The magnitude changes. It's larger over here, smaller over there. It's highly non-constant, and even worse, it's algebraically ugly. So, gosh, we're not happy about the fact that that's the vector field that we're going to be dealing with. Worse, look at the surface now. The surface is, it's lumpy and non-symmetric looking. All sorts of bad things about that surface. I don't even have an equation that helps me describe that surface. So this problem looks almost intractable. It's going to turn out that this has a wonderfully convenient answer. In the first special case that we're going to consider the mass being outside of this closed surface, and as such, here's the beautiful punchline. Keep in mind that we know, I'll do this in pen, I know that the divergence of this gravitational field is 0 everywhere except for where the mass is. So all of here, everywhere over here, the divergence of that gravitational field is 0, including the point throughout the entire interior of the solid. Keep in mind the mass is outside of the solid. So everywhere inside here of the solid, the divergence is 0. And the calculation then works out really nice. The grand total amount of flux, right, is just a triple integral of divergence. We just argued that this divergence is 0 throughout the entire solid because the mass is located on the outside of the solid. So we're doing a triple integral of 0. And therefore, the flux is 0. And that is an awesome result. Again, the situation looked bleak, really bleak. We had this ugly situation, ugly vector field, nondescript, potentially ugly surface, and answer 0 all the time. Wonderful. Okay, well, that's a great calculation. Now, we did make an assumption in this calculation. The assumption was that the mass was on the outside. If the mass is on the inside, that does change things a little bit. So here we go now. Now I'm going to put the mass inside of the surface. That surface still being the boundary of this solid. I'm going to call it R, let's say. Okay, so I can't do that same calculation. I can't just talk about the triple integral of divergence. The divergence isn't even defined at that point. So I can't do a triple integral if my integrand isn't defined. So, right, so what are we going to do? So we're going to make a clever move here. This is a neat trick. The idea is we're going to take this surface and combine it with this surface, S. Between the two of them, we have that they form the boundary of a different solid region. Now it's not R. R is the whole the whole potato there. What we've got here is between those two surfaces, we have the boundary of this thing I'm calling R0. So, boundary of R0 is, well, it's going to include the boundary of R, and it's also going to include S. Now, let's think carefully about signs. This surface S, in order to, well, just to keep it convenient, I'm going to have it oriented outward. The boundary of R also boundary of R also oriented outward. Keep in mind that when you say boundary of R0, we have to talk about boundaries oriented with their normal vectors pointing outside, away from the mass. So if we want to talk about the boundary of R0, that surface, the part of it, the way in which S is part of the boundary of R0 is oriented wrong. S points into the mass, into the region R0, and we need it to be oriented the other way, away from R0. So I have to say minus there. So the boundary of R0 is boundary of R minus S. And this is a wonderful surface because, like in the previous example, the mass is not in that solid. Right? The mass is not in R0. So I can talk about flux through the boundary of R0. I can rewrite that as a triple integral of divergence over R0 because there's no mass in R0. And that's where I get this calculation here. The flux through the boundary of R0, triple integral of divergence through R0, 0. Now, that does not answer our question. That's not what we wanted in the first place. What we wanted in the first place was flux through the boundary of R. Now, the boundary of R is part of the boundary of R0. I've computed that this flux here is 0. The flux through that is 0. Therefore, this difference of two fluxes is what I've computed equal to 0. That difference is equal to 0. And it doesn't tell me what the flux through the boundary of R is. What it does tell me is that these two individual fluxes are the same. If their difference is 0, then they are the same. And that's what we have here. These two fluxes are the same. So the really nice conclusions come from this. Let's look back at this picture. And let's think about what went into this. What are we assuming? Well, this mass, we assumed that it was on the inside. And then I said, well, let's put a little ball around it. But you'll notice I didn't say where on the inside that mass is. The mass could have just as well have been over here. And I could have put a little ball around that. Or it could have been over here. And I could have put a little ball around that. So the nice conclusion is that the flux through the boundary of R, this flux that we're interested in computing, doesn't depend on where the mass is. Wherever the mass might happen to be, you just put a little ball around it. And you're going to end up with the exact same integral and the exact same value. So the neat punchline that we get here is that this value, the flux through the boundary of R, does not depend on where the mass is, or if there are multiple masses, how those masses are distributed. It only depends on the amount of mass. Distribute that mass however you like, doesn't make any difference. So really powerful fact then. So it's flux, boundary flux, is independent of how the mass is distributed. Okay. All right, so that's our second neat conclusion. And again, it's a pretty sophisticated physics fact if you think about it. How would you compute this integral directly? and show that it doesn't matter where the mass is. It'd be a hard calculate. It's a complicated vector field. It's a flux integral. The surface itself is bumpy and wiggly and asymmetric probably, and just all kinds of ugly in that calculation. So the divergence theorem gives us this neat result. Okay. All right. Okay. Next thing I want to consider is a seemingly even harder problem. I'm going to give myself a little bit of room to work here by adding a page. And here's the question that we're going to consider. Now, instead of having a mass at a single point and considering whether that mass is inside or outside of the surface we're interested in, we're going to consider a distribution of mass. And I'm just going to, this is a sloppy way to represent a distribution of mass. But so there's mass sort of all over. It's like a mass cloud. And it's not necessarily of a constant density. So maybe there's more mass over here. There's sort of a double density, and maybe even more mass. Maybe there's sort of a density hot spot the closer you get to this, over here is where most of the mass is, and then there's, very small amount of mass way over there. Okay. Now, how would we understand anything about the gravitational field created by this complex distribution of mass? Well, this has got the potential to be really, really ugly. So let's think about, for example, there's a tiny little piece of mass right there. What could I conclude? About the gravitational field created by that little piece of mass? Well, we have a formula for that. One little piece of mass creates a gravitational field, which is that formula a couple pages back, and it's already kind of ugly. But what's nasty is now we have to consider also that little piece of mass, and that little piece of mass, and all of these little pieces of mass, and don't forget about these masses over here, and then there's, of course, lots and lots of mass. All these little pieces of mass are at different locations, spread around, each one of them generating what is itself a fairly ugly gravitational field. And we have to consider all of them. So, seemingly an intractable problem. And it turns out that in studying this gravitational field, some really, really nice things happen. So let me dive into that. So I'm not gonna compute the actual gravitational field. That is hard in general. What I want to do is compute a boundary flux. So I want to consider a surface. And I'm going to take a small surface, a little small surface there. And I want to compute the flux of this nasty gravitational field through that boundary surface. Okay. Well, we have a couple of really nice results that help us answer that question, or make a lot of progress toward answering that question anyway, very quickly. For one thing, the very first fact we showed is that the mass that's on the outside doesn't matter. If I'm interested in flux through this surface, all of this mass right here doesn't matter. It's all irrelevant. Who cares? It doesn't affect the flux through that surface. Now, there, of course, is some mass. Whoops, there's some mass on the inside here. Oops. Certain amount of mass on the inside. Well, we have a result that relates to that as well. That mass on the inside, sure, it generates some flux through that boundary surface. But it doesn't really matter where in that region the mass is. I could take all this mass and concentrate it right at the center of that sphere. And it wouldn't, the gravitational divergence would still be the same. So we have made tremendous progress towards simplifying this problem just by using these two previous observations. The mass outside of our sphere doesn't generate any flux. The mass on the inside of the sphere can be rearranged to our heart's content, and the flux is still the same. So now, instead of a very, very nasty, complicated problem, we have a single point mass at the center of our sphere, and it's going to create a gravitational field. We know exactly what its gravitational field looks like. It's radially pointing toward the mass. And we've got a pretty good shot at computing this flux at this point. So here's the details of the calculation. So we're going to compute directly that flux is, there's our classical formula from Chapter 5. Let me rewrite that. We're going to use this other form of it. There's our flux from Chapter 5. Note with the gravitational field, we have a formula for that. Here's our gravitational field. Since this surface is a little sphere, the unit normal vector is going to point in exactly the same direction. Whoops! Oh, I need a better color. It's going to point in exactly in the same direction as the position vector describing the point you're at. So in fact, that little n vector is just the unitized version of x. So it's x divided by the magnitude of x. Again, spheres are wonderfully convenient. So there's our normal vector. And so we've got a calculation to do here. We compute that thing. Now that looks kind of ugly, but it simplifies really nicely. Notice that x dot x is magnitude of x squared. Note also that the magnitude of x is r because we're looking at a sphere, some little sphere of radius little r, and so all the points on the sphere, magnitude of x is always that same value. So really what we have in this expression here, all of this ugly here, is just r squared divided by r to the fourth, which is 1 over r squared. Negative gm factors right out as well. R being a constant, we can factor it outside of the integral. And that gives us then really nothing left to integrate. We just have the surface area of our sphere. Surface area of the sphere is old news, old formula from geometry class. And the r squareds cancel, and we're left with a really simple formula for that flux. Wonderful result here. The flux through that little tiny sphere is constant, certain constants, negative 4 pi g, times the grand total amount of mass in that little sphere, and that's it. And again, it doesn't matter how the mass is distributed inside the sphere. It only matters what the total amount of mass is in that sphere. Okay. Now, we're not really quite done. We're going to get an even better result by taking an alternative point of view on this. We just computed the amount of flux through this little sphere here. We just computed that flux. And keep in mind, flux is also something you compute with Gauss's divergence theorem. And again, in this case, we're considering a really small sphere, and if it's a really small sphere, then we're going to treat divergence as a constant, let it factor out. The remaining integral dv is just the volume of that sphere. And altogether then, flux, I've just computed it two different ways, and so the two different answers I've gotten are the same. And solve for divergence, and divergence is negative 4 pi g, and then we have m over v, which of course is density. So this is an amazing, really amazing little calculation. We have this very complicated gravitational field. So complicated we're not even going to begin to try to actually write down that gravitational field. It's created by all these little point masses located in different places. There are infinitely many of them, each one generating itself an ugly gravitational field, and yet the divergence is a simple formula. And it's just proportional to mass density, which is, again, just a shocking result. Wonderful result there. Okay. By the way, this gives a kind of a nice way to think about gravity. You look at this. Let me rewrite this a little bit, actually. Keep in mind, divergence we've already talked about being flux density. Well, delta, that's mass density. And what this is saying is that flux density is proportional to mass density, or said differently, flux, the flow of fluid, the fluid that's being generated here, that's flowing through our surface, that fluid is generated by mass. If the amount of the flux generated in a given region is proportional to the amount of mass in that same region, then it makes it look like the flux is being created by the mass. This is kind of suggestive of a point of view that's in use in physics, and that is that we talk about gravitons as little particles. And the idea is that mass, as it sits there, is shooting gravitons out of itself, kind of like photons out of a light bulb. And these gravitons are the way that gravitational force is communicated. This is the metaphor, that is. That mass communicates gravitational force by the emanation of these gravitons. And with that in mind, the gravitational field is the flow field of this fluid of gravitons. And the flux is generated by mass, and so the divergence is proportional to mass density. So it's a really wonderful fact that this formula creates a motivation for a way to think about gravity, sort of a physical theory. Really neat fact. Okay. Well, this isn't a physics class, and so I'm not going to spend too much time on that. Okay. Now, this is a local statement. So, in particular, this tells you what the divergence is at a particular point. Divergence is proportional to mass density. We can turn this into a global statement by asking, what's the flux through the boundary of a region. If the gravitational field, if flux is a triple integral of divergence, and if divergence is proportional to mass density, then you'll notice when these factors and these constants factor out, what we end up with is a triple integral of mass density, otherwise known as mass. So another really nice formula here. If you have a surface, mass distributed, however, is strewn about in whatever way, creating a gravitational field that's untold complicated, the boundary flux of that extremely complicated gravitational field is just a very simple formula here, -4 pi gm. So said differently, it's proportional only to the mass that's on the inside. Okay. So a quick example. If you imagine a sphere here, let's say outward-oriented sphere, centered at the center of the sun, and with a certain radius, I could ask, what's the total gravitational flux through that sphere? Well, it's arguably, again, at first glance, a complicated question, because the sun's creating a gravitational field. So is Mercury. So is Venus. So is Earth. So is, well, let's see, Mars is outside of that sphere. But then the Earth's moon is creating a gravitational field as well. And that's most of the mass. Most of the mass inside of this sphere of that radius of 100 million miles is in those objects. So since flux is a simple formula from total mass, you just add up those masses and multiply by negative 4 pi g, and there you go. There's your gravitational flux. Okay. All right, so nice example. So I have one more gravity example that I think is really interesting. Here's the picture for this next gravity example. And we speculate on the possibility that we have a shell of mass. So it's not like a planet exactly. There's a bunch of mass on the outside, and then it's hollow in the middle. And there's just nothing in there. So this is some sort of a weird space station, Death Star kind of thing. And all the mass is on the outside shell. Okay. So, well, if you have a point there, and you want to know how much gravitational field is created, well, that'd be a question to compute. Certainly all these little pieces of mass are pulling you in vaguely that direction, some a little off up, some a little off down, but maybe a bunch of particles pulling you in that direction. So clearly the gravitational force on the outside is a radial pointing exactly at the origin. We're assuming that this is a spherically symmetric shell. Okay. What about on the inside, though? And this is where it gets a little confusing. Imagine a point there. And what's the total gravitational field at that point? The awkward thing is that these pieces of mass over here are pulling it, kind of generally that way, while these pieces of mass over here are pulling sort of generally that way. So, awkwardly, we have opposing forces here. And it's not clear which one is going to kind of win that little tug-of-war. On the one hand, it's tempting to say that, well, these little pieces of mass here are a lot closer to that point. So, using the 1 over distance squared concept, we feel like, well, the closer masses probably have a stronger gravitational pull, and therefore this will be some negligible calculation. However, even though these pieces of mass out here are further away, look how much more of it there is. It's a lot more mass. Each piece of which is pulling less hard, but there's more of it, and all of a sudden we have a really kind of not clear tug-of-war of forces acting on this point right here. Okay. So what we're going to do here is we're going to compute the gravitational field as a function of a location on the inside of the shell, and it has a wonderfully convenient answer. Okay. Right. So here's a point. We're going to use that point. At that point, again, my goal is to find the gravitational field. Right off the bat, I don't know, but I can make a couple of qualitative observations. The first observation I want to make is that it has to point, maybe I'll use the tensor for this, it has to point toward the center. Let's say the center is the origin. It's got to point radially, like that, to the center, because it's a symmetric shell, right? And being as a symmetric shell, I'm not going to make too rigorous of an argument here, but I appeal to your physical intuition. If you have a symmetric object like that, that's going to make a symmetric gravitational field. And then likewise, another symmetry argument, if I were to look over at a different point that's exactly the same distance away, well, what could I say about those two? I didn't draw that very well. I did that even worse. It's hard to see what I'm doing here. Yeah. Anyway, good enough. What could I say about those two field vectors. Well, now they're pointing in different directions, of course. Again, they both got to be radial, despite my inability to draw it. So, but which one's stronger? Well, they're the same distance away, and again, if it's a symmetric shell and the mass is distributed around that outside of the sphere in a symmetric manner, then you really would expect the gravitational pull would be only a function of that distance. Okay, so that motivates this first formula that I'm going to write down. This first formula says that the gravitational force is radial. Radial, so it's got to be pointing in the direction of the position vector, and the magnitude depends only on distance from the origin, and that's the spherical coordinate rho there. Okay, so that's our starting point. All right. Now the next thing I'm going to do is I'm going to take that formula. I'm going to erase this, it's distracting. I'm going to take that formula, and now I want to compute the amount of flux through that sphere. So it's not the shell itself. It's not the shell that has the mass on it. It's this shell, it's this sphere centered at the origin that goes through the point where I'm interested in the gravitational field. So that's what I'm actually interested in, and that point is on a certain sphere centered at the origin. So let's compute the gravitational flux through that sphere. Right. Okay, well, so we know what the gravitational field is. At least we have a qualitative description of the gravitational field. It's got to be radial. It's got to point toward the origin. It's got to be a function only of distance from the origin. And we also know something nice about the normal vector. That normal vector, being that as this is a sphere, points also radially, because spheres are symmetric. So it's not going to point off at some random angle. It's pointing in the exact same direction as the gravitational field, exact same direction as the position vector. So altogether then, this dot product is just rho, because x, the position vector, is rho in. X, the position vector, is a vector that points in the, again, it has to point in that, in the direction that it's pointing, and its magnitude is the distance from the origin. So x is rho times n. So in here we have n dot n. N is a unit vector, so that gives you a 1. That's just the rho. Right. So this f of rho pops outside of the integral because it's constant. It depends only on rho. Rho is constant over the entire sphere, because it's a sphere. And this rho factors out as well. We're left only then with surface integral ds. We're left with just the surface area, which is 4 pi rho squared. And altogether then our answer, there's a bunch of little details here, but altogether our answer is this. That's what flux is. Now again, not what we were interested in. What we want to know, what we're really interested in, is what is the gravitational field. I've got a qualitative description, but I want to know exactly what is it. We don't have that. We've computed flux, because we could. It's something we had, we've had good luck with this in the past. Flux tends to be easier to compute than the gravitational field itself. So what I'm going to do now is compute the flux again in a different way, and that is to come down here and take advantage of our big result that says that if you have a surface and you want to know the gravitational flux through that surface, that gravitational flux has to equal the grand total amount of mass inside of that surface? Well, there is no mass in that surface. The mass is all out here. The mass is all outside of the sphere in question. Because by assumption, the point that described our sphere for us in the first place is inside of the shell. Therefore, the shell is outside of our green sphere. So, no mass, no flux. So, on the one hand, flux is that formula. On the other hand, it is also zero. And therefore, this expression here is zero. And that means that this quantity, f of rho, also zero. And therefore, the gravitational field is zero. So that's an amazing punchline. Very unexpected, even. I don't know, somewhat unexpected. I mean, we had this argument about how, opposing forces, and at this point, this mass is going to be pulling that way, and this mass is going to be pulling this way, and pros and cons of which one might have the stronger forces. So we knew that there were potential canceling terms, but what's amazing is that they have canceled exactly. Okay, wonderful result. Okay. There's some exercises at the end of this section where you're going to make arguments analogous to this, where you have symmetric things, and you make an argument where you, much like this, but with details appropriate to those examples, of course. Okay. All right, so that's all I'm going to say about gravity. Directly, I want to move on now and talk about electric fields. And here's the wonderful good news. Look at this formula for the electric field, for the electric force. Notice it looks awfully similar to the formula for gravity. Specifically, it's inverse square. It's inverse square, just like gravity is. It's proportional to the product of the two charges in question. Well, that's not that different from mass. With mass, it's proportional to the product of the two masses to give you the gravitational force. So this is analogous, different physical manifestations, but really structurally, in terms of the model we're writing down here, it looks awfully, awfully similar. And then, there's some other objects in here. There's this 4 pi and epsilon naught. That's just a constant. So there are different constants involved, but constant factors tend not to make much of a difference when you go through calculations. They just carry along with all the various derivatives that you would take, etc. So, in fact, the way that you analyze electric fields is extremely similar structurally to the way that you analyze gravitational fields. In fact, all of the results that we've talked about for gravitational fields, there are analogous results for electric fields. So what I like to tell students is that when you're thinking about electric fields, and now, of course, electric fields are arguably more important. If you're an engineer, you're going to build things that use electric forces. Not a lot of gravitational. I mean, the force of gravity at the surface of the Earth is pretty much constant, so you don't really need to understand the complications of gravitational fields for engineering purposes most of the time, unless you're involved in space exploration. If you're building the next, rocket or a space shuttle or something, then yeah, sure, absolutely. But for most products, gravity is pretty simple. Right? The point, then, to all of that talk about gravity is that it is a physically relatable metaphor for understanding electric fields. Electric fields we know what they are, and we've seen formulas for them, but they're hard to relate to physically. You can't feel an electric field very well. You can feel gravity very well. You can't feel electric charge exactly. It's hard, you can't see it exactly. Mass, on the other hand, is extremely relatable, right? So I think this is a good reason to start with the gravitational calculations that we just got through doing, and very, very similar results come through for electric fields. So in particular, here's a series of arguments that we made for gravity. They all work for electric fields as well. Here are the equations. There's a formula for your electric field generated by a single charge Q at the origin. You can compute the divergence in the same way that after a series of arguments we concluded that gravitational divergence was proportional to mass density. Likewise, electric divergence is proportional to charge density. Because charge is playing a role analogous to mass when you're studying electric fields. And taking a triple integral of both sides, electric flux is proportional to the amount of charge on the inside. And again, all the wonderful results that we had with gravity come along with this one. So charge that is outside of your surface doesn't matter. Charge that is inside of your surface matters only in how much of it there is, not in where it is, not in how it's distributed. So again, really, really neat result there. Okay. Now I'm going to say a quick word about Maxwell's equations. So this is one of Maxwell's equations. This is the differential form of what I'm going to call Maxwell's first equation, arbitrarily. The ordering doesn't matter. So it's a statement about the divergence of the electric field. Well, we call this the differential version because you can see a derivative right there in it. There is another version of this theorem, what we call another version. It looks like, in fact, a different theorem. It looks like a different equation. But it's really, really, in fact, pretty similar. The idea, then, the way that you relate these two seemingly different results is by Gauss's divergence theorem. So specifically, take a triple integral of both sides. I'm going to abuse notation here. So let's take a triple integral of both sides. A triple integral of divergence of the electric field is the flux of the electric field. There's Gauss's divergence theorem. Flux is a triple integral of divergence. On the other side, now I have there's a constant in the way, but other than that, there's a triple integral of charge density. And triple integral of charge density gives you, well, let's leave that constant in. Charge. So that denominator constant comes along for the ride. Very immediate connection in the context of Gauss's divergence theorem. Without Gauss's divergence theorem, it's hard to make this connection. They look like really different results. So I like to point out, and this is very important for those of you who are in physics or engineering or anything where you're going to be studying electric fields, that the different versions of Maxwell's equations, the thing that makes them different versions of the same equation as opposed to just different equations, is Gauss's divergence theorem. So understanding Gauss's divergence theorem is critical for having a good understanding of how electric fields work and how physics of electric fields works, related to engineering, things that you can do with that. Okay. There's a similar fact that you can say about magnetic fields. Now, we're not going to talk about magnetic fields in this course. It's not a physics course, and it takes some time, and there's some weird things about it. We're going to do a few things with it, but very little. But one result is that the divergence of the magnetic field is 0. So now again, there's another version of that. The flux of the magnetic field through a boundary surface is 0. Now they look like totally different things. I mean, these two things here they're certainly not the same thing, and the fact that they're both zero could be viewed as two entirely separate statements. But again, these relate very closely to each other. If you take bad handwriting, if you take a triple integral of both sides, again, I'm using notation here, you end up with a triple integral of divergence, which is flux, and that's what turns this divergence statement into this flux statement. Said differently, that's what turns this differential form of Maxwell's second equation into this integral form of Maxwell's second equation. Okay, a lot of neat physics that connects to all of that. Okay, so this very last subsection is on a version of Gauss's divergence theorem in R2 instead of R3. I'm going to leave the details for you guys to do on your own. It's not much here. The main bit of work is to argue that if you're interested in computing flux through the boundary curve of a two-dimensional region, that flux is an accumulation of the fluxes through the boundary curves of the little pieces that you would break your region up into. The main tool that goes into observing that is this cancellation argument. So if you look at this edge, that's part of the boundary that gets created when you chop it up. Thought of as part of the boundary of that region, it's oriented that way. Thought of as part of the boundary of this region, it's oriented that way. And so this edge is going to appear in the summation twice, but with opposite orientations, and therefore those two fluxes cancel and proceed. Everything else is analogous to what we did in the three-dimensional version. Again, I'm going to let you guys read through the details, but it's very analogous. And in fact, even the result, the formula, here's our two-dimensional divergence theorem, the formula for divergence that we write as divergence still looks like a dot product with the del operator. So it's written down in seemingly exactly the same way. Okay. All right. Well, that's a good place to stop. And next time we will pick up with Stokes' curl theorem. Okay.